to withstand some of the following specific hazards, like the temperature should be in the limit, what will happen if it fails. We have to consider each and everything, like the worst case pressure gradient associated with the most critical scenario for detonation of liquid or solid rocket propellant. Safety issues with the design sketch. This is we had to stop the testing there because there were some safety issues with the designs. Like from some of the engines, radioactive particles were coming out of the engine. And secondly, the public was not aware of it. And thirdly, but not the most importantly, the proper sealing materials were not available for sealing our radioactive particles. This is a layout on which our future nuclear power engines and standards can work. This is a nuclear reactor core which is shielded by a radiation shield which can act as a black box. We have to develop it, but which can act as a black box in case of any failure. Heat from the nuclear reactor core is taken away by the coolant and taken into the engine's combustion chamber, where heat is transferred to the flowing propellant and we get the desired thrust at the output. This is the working of the nuclear power scramjet engine is almost the same as that of a ramjet engine. Velocity of incoming air is decreased by the diffuser section. Heat addition we do by the help of heat exchangers inside the combustion chamber section, so that we will get a desired thrust at the output. Just following case study, I have studied one ramjet engine working on chemical combustion systems and other on nuclear energy. We are given the same dilution and operating conditions through the CFD software. Left hand side plot is according to the normal combustion, and right hand side we had used inputted heat by the help of heat exchangers. In both the cases, operating conditions were same. Operating conditions were same for the chemical combustion ramjet and nuclear power ramjet. Dimensions of both engines were same. In nuclear power ramjet, we had used heat exchangers for heating the propellant. Both the engines are given comparable velocity and thrust. Velocity in both the engines we are getting around 1100 meters per second. This is according to our design. The heat exchanger used to carry out heat addition is a plate type heat exchanger which we have used in this design, as this reduces the blockage in flow, hence reducing the unnecessary shocks and expansion waves in the combustion chamber. It was observed that jet leaking out of a nozzle in a nuclear power ramjet was much more circular and wide, occupying the entire cross section and diverging part of the nozzle, as we have also observed in our design. This is a schematic how we can hybrid our ramjets and scramjets with nuclear energy. We can firstly heat the incoming air by help of nuclear energy inside the engine combustion chamber. Then, in the later part, we can do standard chemical combustion, standard chemical supersonic combustion, as we normally do in our scramjet engines, so that we can get the desired output. By this way, we can increase our efficiency of our present engines a lot. High temperature combustion and hybrid zone is a major area of research these days, and it will be there in the future also because we need to increase our efficiencies a lot. These are some of the applications of such engines like aircraft, target drones, anti-aircraft guided missiles and space applications. Now coming to the conclusion. In this presentation, I have attempted to cover the most significant design issues and concepts in the field of nuclear thermal propulsion. This technology, in whatever form it finally takes, appears necessary to meet our nation's commitment to the goal of its space exploration initiative. It is clear from the presented material that there are significant advantages in developing nuclear thermal rockets. The rich history of analysis and testing of nuclear thermal rockets concepts and design provides foundation upon which current design concepts are based. The future of this particular technology rests in adequate funding for the continuation of the research and commencement of construction and testing phase for more advanced designs. In addition, major efforts to educate people must be made to avoid public policy, mandate to end the nuclear thermal rocket propulsion program without an opportunity to test and deploy. The role of the safety in all phases of development must be emphasized in the government and industry segment, closely connected with the efforts to explore space. There are a large number of professionals who strongly believe that our ability to begin serious exploration and settlement of our solar system could depend on this nuclear propulsion program. From the data available, it seems that this sentiment is correct.